You are sitting somewhere right now, maybe in bed, maybe on a train, maybe in an office where fluorescent lights hum above you, and you have not thought about the ceiling in months. You feel safe. You feel like tomorrow will come, and next week and next year. You feel like humanity has survived ice ages and plagues and world wars, and surely we will keep surviving. But what if every intelligent species in the history of the universe felt exactly the same way? What if they all sat somewhere, comfortable and certain, right before they vanished? The stars that burn above you tonight are ancient. Many are billions of years old, far older than our sun, far older than Earth. If intelligent life arose on planets orbiting those stars even a fraction of their history ago, those civilizations would have had millions or billions of years to spread across the galaxy. They could have visited every star. They could have built structures visible across light years. They could have made themselves impossible to miss. But when we look, we see nothing. When we listen, we hear silence. The cosmos stretches before us in perfect, pristine emptiness. Where is everybody? That question, asked by physicist Enrico Fermi over lunch in 1950, has haunted scientists ever since. Not because the answer is hard to find, but because every possible answer is disturbing. Either intelligent life is so rare that we are alone in a universe of 2 trillion galaxies, or intelligent life arises regularly and something destroys it before it can spread. The silence is trying to tell us something, and what it is saying might be the most important thing humanity has ever needed to understand. To understand what the silence means, we must first understand what we should see. In the 13.8 billion years since the Big Bang, the universe has produced an estimated 2 trillion galaxies, each containing hundreds of billions of stars. That is a number so large it loses meaning. A 1 followed by 24 zeros. More stars than grains of sand on every beach on Earth. And yet, when we point our most sensitive instruments at the sky, when we listen for signals across 60 years of searching, we hear nothing. We see nothing. The universe is silent. Stop and think about what that silence means. Our galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. Current estimates suggest it is roughly 100,000 light years in diameter, a number that itself stretches comprehension. Light, traveling at 186,000 miles per second, takes 100,000 years to cross from one side to the other. And the Milky Way is not special. It is one spiral galaxy among hundreds of billions. The Andromeda Galaxy, our nearest large neighbor at 2.5 million light-years away, contains roughly 1 trillion stars. The Virgo supercluster, of which our galaxy is a tiny part, contains over 2,000 galaxies. The observable universe stretches 46.5 billion light-years in every direction. Within this inconceivable vastness, the conditions for life appear to be common. The same elements that comprise our bodies, carbon, hydrogen, oxygen, nitrogen, are abundant throughout the cosmos. They form in the hearts of stars and are scattered across space when those stars explode. Every atom of carbon in your body was forged in a stellar furnace billions of years ago. Water, once thought rare, now appears ubiquitous. We have found evidence of water ice on the Moon, on Mars, on the moons of Jupiter and Saturn. Comets are essentially dirty snowballs. Water is not a precious anomaly. It is cosmic commonplace. This is not philosophy. This is physics. And the math suggests something has gone terribly, terribly wrong. To understand why the silence should terrify you, we need to start with what the silence implies. The numbers should work in favor of life. They overwhelmingly should. The observable universe stretches 46.5 billion light-years in every direction. Within that sphere exists roughly 1 septillion stars, a number written as 10 to the 24th power. NASA's Kepler Space Telescope, which operated from 2009 to 2018, revealed that planets are not rare exceptions, but cosmic commonplace. Analysis of Kepler's data showed that between 20 and 50% of stars likely host Earth-sized rocky planets in their habitable zones, the orbital distance where liquid water could exist on a planet's surface. The Kepler team estimated there could be as many as 40 billion rocky planets in habitable zones just within our Milky Way galaxy alone. Our own planet formed 4.5 billion years ago. Life appeared astonishingly quickly after conditions allowed, perhaps within the first 500 million years. Within 3.8 billion years, single-celled organisms had colonized the planet. Within 4 billion years, multicellular life had emerged, and within 4.5 billion years, a species had developed nuclear weapons, sent probes to other planets, and begun scanning the cosmos for signs of intelligence. If this progression happened once, on one planet, around one unremarkable star, then it should have happened countless times throughout a universe that is nearly 14 billion years old. Stars formed billions of years before our sun was born. Planets coalesced around those ancient stars billions of years before Earth existed. Any civilization that emerged on one of those worlds would have had billions of years of head start. Think about what that implies. A civilization with even 1 million years of technological development beyond us, let alone 1 billion years, should be unimaginably advanced. They should have spread across the galaxy. They should have constructed megastructures that block starlight. They should have sent probes that have reached every star system. They should have transformed the cosmos in ways we cannot even imagine, but certainly could detect. 1 million years sounds like an unfathomable span, but in cosmic terms, it is trivially short. The sun has existed for 4.5 billion years. A civilization with 1 billion-year head start on us would have had time to colonize every star in the galaxy 1,000 times over, even traveling at only a fraction of the speed of light. Physicist Freeman Dyson proposed in 1960 that an advanced civilization might construct a shell or swarm of collectors around its star to capture most of its energy, a structure now called a Dyson sphere. Such a structure would be invisible in visible light, but would radiate strongly in the infrared as waste heat. We have surveyed millions of stars looking for such signatures. We have found none. Self-replicating probes, machines that could travel to a star system, harvest resources, build copies of themselves, and send those copies to nearby stars, could colonize an entire galaxy in less than 1 million years, even at speeds achievable with technologies we can imagine today. Once launched, such a program would be essentially unstoppable and would reach every star system in the galaxy. We have found no evidence of such probes in our own solar system. Radio technology has existed on Earth for about a century. For that entire century, we have been broadcasting our presence to the cosmos, a sphere of radio noise expanding outward at the speed of light, now roughly 100 light-years in radius. Any civilization within that sphere with equivalent technology could detect us. Any civilization with more advanced technology could likely detect us from much farther away. Yet when we look, we see nothing but dead matter following simple physical laws. No megastructures, no artificial signals, no probes, no evidence whatsoever that anything intelligent has ever disturbed the pristine emptiness of space. In 1950, the Nobel Prize-winning physicist Enrico Fermi sat down to lunch with colleagues at Los Alamos National Laboratory. They had been discussing flying saucers and the feasibility of interstellar travel. Fermi, known for posing deceptively simple questions that cut to the heart of complex problems, suddenly asked, "Where is everybody?" His colleagues remembered the question differently over the years. Edward Teller recalled it as, "Where is everybody?" Emil Konopinski remembered, "Don't you ever wonder where everybody is?" Herbert York confirmed the conversation happened, though the exact date had been forgotten. What they all remembered was the profound weight of the question. Fermi was not being casual. He had done calculations in his head, as he was famous for doing. Given what was known about the age of the universe, the number of stars, the likelihood of planets, the time required for evolution to produce intelligence, and the time required for an intelligent species to colonize a galaxy, there should be evidence of extraterrestrial visitors or signals everywhere. The absence of such evidence was not merely disappointing. It was deeply strange. It was, as it came to be called, paradoxical. In the decades since that lunch, we have learned much that should have resolved the paradox. We have confirmed that planets are ubiquitous. We have found thousands of potentially habitable worlds within just a few thousand light years. We have developed technologies that can detect artificial signals from across the galaxy. We have searched and searched and searched, and we have found nothing. Given the age and size of the universe, given the apparent ubiquity of habitable worlds, given the relatively short time it took intelligence to evolve on Earth, where indeed is everybody? The question became known as the Fermi paradox, though Fermi himself may not have considered it paradoxical so much as a pointed observation about our cosmic solitude. The question first appeared in print in a 1963 paper by Carl Sagan, and by 1975, physicist Michael Hart had published a detailed examination concluding that we might be alone in our galaxy. In 1961, 10 years after Fermi's lunch conversation, astronomer Frank Drake convened the first scientific meeting on the search for extraterrestrial intelligence at the Green Bank Observatory in West Virginia. To structure the discussion, Drake wrote an equation on the chalkboard. It was not meant to provide a precise answer. It was meant to organize thinking about an almost impossibly complex question. The Drake equation estimates the number of communicating civilizations in our galaxy as the product of 7 factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per star system, the fraction of habitable planets that develop life, the fraction of life-bearing planets that develop intelligence, the fraction of intelligent species that develop detectable technology, and the average lifetime of a technological civilization. At the 1961 meeting, Drake and his colleagues, including physicist Philip Morrison and a young postdoctoral researcher named Carl Sagan, plugged in their best guesses. For some factors, like the rate of star formation, they had reasonable estimates. For others, like the fraction of life-bearing planets that develop intelligence, they were essentially guessing. Their calculations suggested somewhere between 1,000 and 100 million technological civilizations might exist in the Milky Way at any given time. Even the lower bound seemed to promise a galaxy teeming with intelligence. But 60 years later, the Drake equation has yielded answers far less optimistic than its creators hoped. We now know some factors better than Drake did. The Kepler mission confirmed that planets are common. Virtually every star has at least one. But we have learned nothing about the most critical factors, the ones that determine whether life arises, whether it develops intelligence, whether it survives. The factor that most concerned the attendees at that 1961 meeting was L, the average lifetime of a communicating civilization. This variable encapsulates everything that could destroy a technological species: nuclear war, environmental collapse, asteroid impacts, artificial intelligence run amok. If L is large, if civilizations typically survive for millions or billions of years, then the galaxy should be filled with them. If L is small, if civilizations typically destroy themselves within centuries of developing radio technology, then at any given moment, the galaxy might contain only a handful of technological species, briefly flickering into existence before vanishing. Philip Morrison, who had worked on the Manhattan Project and watched the first atomic bomb explode in the New Mexico desert, suggested that L might be very small indeed. He estimated that if civilizations typically lasted only about a decade after developing nuclear weapons, there might be only one technological civilization in our galaxy at any given time. That civilization would be us, and we would be alone. Drake's personal estimate was more optimistic. He suggested L might be around 10,000 years, implying perhaps 10,000 civilizations scattered throughout the Milky Way. But even this optimistic scenario presented a problem. If 10,000 civilizations exist in a galaxy of 100 billion stars, the average distance between them would be thousands of light years. Communication would be effectively impossible. We would be surrounded by neighbors we could never meet. And if Morrison was right, if L is only a few decades, then we are witnessing the last gasp of the only technological civilization to arise in this galaxy, and perhaps the last to arise ever anywhere. And we have observed something Drake did not anticipate, a universe that appears utterly, inexplicably empty. But it was economist Robin Hanson who, in 1996, gave the most disturbing framing to Fermi's question. If the universe should be teeming with advanced civilizations and is not, then something must be stopping civilizations from reaching that advanced state. Something must be filtering them out. Hanson called it the Great Filter. The Great Filter is not a wall or a barrier in any physical sense. It is a probability threshold, a step in the development from dead matter to a spacefaring civilization that is so improbable, so nearly impossible, that virtually no civilization makes it through. The filter could be a single catastrophic event, or it could be the cumulative improbability of many difficult steps compounding together until the odds become astronomically small. To understand the filter's power, consider the math. Imagine you roll a die a trillion times. If the filter lets through 1 in a million civilizations, you would expect to see a trillion divided by a million successful civilizations, which is still a trillion. Even with an extremely severe filter, this should produce observable civilizations throughout the cosmos. But we see 0, not 1, not a handful, 0. This means the filter is not 1 in a million. It is not 1 in a billion. The filter must be so severe that out of all the potential starting points for technological civilization in the observable universe over the entire 13.8 billion year history of the cosmos, effectively none have made it through to a stage where they would be detectable to us. As Hanson wrote in his original paper, humanity seems to have a bright future, a non-trivial chance of expanding to fill the universe with lasting life. But the fact that space near us seems dead now tells us that any given piece of dead matter faces an astronomically low chance of begetting such a future. There thus exists a great filter between death and expanding lasting life. The math is ruthless. With trillions of planets potentially hosting life over billions of years, even a filter that lets through 1 in a billion civilizations should have produced thousands of detectable civilizations by now. The fact that we detect 0 means the filter must be letting through far, far less than 1 in a billion. Perhaps 1 in a trillion. Perhaps 1 in a septillion. Perhaps only 1, ever, in the entire observable universe. The critical question, the question that determines whether we should feel hope or despair, is where the great filter lies. If the filter is behind us in our evolutionary past, then we have already beaten the odds. We are the rare winners of a cosmic lottery, improbable beyond measure, but here nonetheless. The universe is empty because life almost never gets started, or almost never develops complexity, or almost never produces intelligence. We are the exception that proves the rule. But if the filter is ahead of us in our future, then our apparent success is meaningless. Every civilization that reached our level of development felt the same sense of achievement we do. They marveled at their own improbability. They assumed they were special. And then something destroyed them. Understanding which scenario we face requires examining where the filter might be located along the path from dead chemistry to cosmic civilization. The journey from simple matter to spacefaring intelligence involves what scientists call major evolutionary transitions. Each transition represents a step that had to occur for us to be here, and each step might be the filter. A 2020 paper in the journal Astrobiology by researchers including Andrew Snyder-Beatty and Anders Sandberg analyzed the timing of major evolutionary transitions on Earth to estimate how difficult each step was. Their method was elegant. If a transition occurs quickly relative to the time available, it was probably easy. If it takes nearly all the available time, it was probably hard. Their conclusion was sobering. The expected time for each transition to occur likely exceeds the lifetime of Earth, perhaps by many orders of magnitude. Even when abiogenesis is assumed to be common, the posterior probability assigned to the set of parameters that would allow all transitions to occur successfully within Earth's lifetime was only 16% for a generous set of assumptions and as low as 1/10 trillionth for stricter ones. Consider the first step, the origin of life itself. Abiogenesis, the emergence of living systems from non-living chemistry, remains one of science's most profound mysteries. We know life appeared on Earth relatively quickly in geological terms, perhaps within 500 million years of the planet becoming habitable. This might suggest life is easy, almost inevitable, given the right conditions. But this reasoning contains a subtle trap. In 2012, David Spiegel and Edwin Turner of Princeton published a Bayesian analysis of what life's early emergence on Earth actually tells us about its probability elsewhere. Their conclusion was disturbing, because we could only exist to observe our own origins if life had in fact emerged and eventually produced us. The early appearance of life on Earth is consistent with abiogenesis being extremely rare. We are necessarily observing from a biased position, from a world where it worked. We cannot observe the trillions of worlds where chemistry churned for billions of years, and nothing happened. The origin of life requires the emergence of self-replicating molecules capable of carrying and transmitting information. The simplest such molecules we know, RNA strands capable of self-replication, would need to be at least 40 to 100 nucleotides long to function. The probability of such a molecule forming by random chemical assembly is vanishingly small. A 2020 paper in Scientific Reports calculated that a universe many orders of magnitude larger than our observable one might be required to expect even a single such molecule to form by chance. Perhaps life on Earth did not form by pure chance. Perhaps there are chemical pathways, selection mechanisms we do not yet understand that make the process more likely. Or perhaps we are the result of the most improbable chemistry imaginable, winners of a lottery that never pays out twice. The emergence of the eukaryotic cell, approximately 1.8 to 2 billion years ago, represents another potential filter. For roughly the first half of Earth's history, all life was prokaryotic, simple cells without a nucleus or organelles. Then, in a single event that appears to have occurred only once in 4 billion years of evolution, one prokaryotic cell engulfed another, and instead of digesting it, integrated it. The engulfed cell became the mitochondrion, the powerhouse that enables the complex energy metabolism of all plants, animals, and fungi. The fact that this endosymbiotic event appears to have happened exactly once, despite billions of years of opportunity, suggests it might be extraordinarily improbable. Dirk Schulze-Makuch and William Baines, astrobiologists who have extensively studied the evolution of complexity, note that while convergent evolution shows some traits evolving multiple times, the eukaryotic cell appears to be genuinely unique. Nick Lane, a biochemist at University College London who has written extensively about the evolution of complexity, argues that the energy constraints on prokaryotic cells fundamentally limit their complexity. Prokaryotes generate energy across their outer membrane. As a cell grows larger, its volume increases faster than its surface area, meaning larger prokaryotes cannot generate enough energy to support complex operations. The mitochondrion solved this problem by providing internal energy-generating membranes that scale with cell volume. This solution, Lane argues, was essential for the evolution of complex life. Without mitochondria, there could be no large cells, no cell differentiation, no multicellular organisms, no brains, no intelligence. And yet this solution evolved only once, suggesting it might be extraordinarily difficult. Then there is the emergence of multicellular life. Here the picture becomes more optimistic. Multicellularity has evolved independently at least 40 times on Earth, suggesting it might be a relatively easy transition once complex cells exist. Plants, animals, fungi, and several groups of algae all evolved multicellularity separately. The basic toolkit for cell adhesion and communication appears to predate the split between these lineages. But the emergence of intelligence, true technological intelligence capable of reshaping its environment, appears to have happened only once. Dolphins are intelligent, crows are intelligent, octopuses are intelligent, but only humans build radio telescopes and nuclear reactors. The late paleontologist Stephen Jay Gould famously argued that if we could rewind the tape of life and play it again, the results would be radically different. Intelligence of the human variety, he suggested, was not an inevitable outcome of evolution, but a contingent accident dependent on a long chain of improbable events, any one of which could have gone differently. This suggests intelligence of the civilization-building variety might itself be extremely rare, a quirk of evolution that required an improbable chain of contingent events. The right brain structure, the right body plan, the right environment, the right selection pressures, all converging at the right time. Peter Ward and Donald Brownlee, both of the University of Washington, formalized this perspective in their 2000 book, Rare Earth: Why Complex Life is Uncommon in the Universe. They argued that while microbial life might be common throughout the cosmos, the specific conditions required for complex life, including plate tectonics, a large moon to stabilize orbital tilt, a position in the galactic habitable zone away from sterilizing radiation, and a host of other factors, might be vanishingly rare. Their argument is detailed and sobering. Consider plate tectonics. On Earth, the movement of continental plates drives the carbon cycle, regulating atmospheric CO2 over geological timescales. Volcanic activity at plate boundaries releases carbon dioxide, while weathering of exposed rock removes it. This thermostat has kept Earth's temperature relatively stable for billions of years, despite the sun growing 30% brighter. Without plate tectonics, Earth might have suffered the same fate as Venus, where runaway greenhouse warming turned the surface into a 900-degree hellscape. But plate tectonics requires a planet of the right size, with the right internal heat, with the right mantle viscosity. Too small, and the planet cools too quickly, and tectonics stop. Too large, and the crust becomes too thick and rigid to move. Is Earth's size coincidence or cosmic necessity? Consider the Moon. Earth's moon is unusually large relative to its planet, about a quarter of Earth's diameter. It formed from a giant impact approximately 4.5 billion years ago, when a Mars-sized body struck the young Earth. This impact also tilted Earth's axis of rotation, giving us seasons. But more importantly, the Moon's gravitational influence stabilizes that tilt, preventing it from chaotically varying over millions of years as Mars's tilt does. Without the Moon, Earth's climate might have fluctuated so wildly that complex life never had time to evolve. Consider Jupiter. The giant planet acts as a gravitational vacuum cleaner, capturing or deflecting many comets and asteroids that might otherwise strike the inner planets. Without Jupiter, the impact rate on Earth might be orders of magnitude higher. Complex life might be sterilized by impacts before it ever has a chance to develop. Consider our position in the galaxy. We are located in the Orion Arm, roughly 2/3 of the way from the galactic center to the edge. The galactic center is a dense, violent place, with stars passing close to one another, supernovae occurring frequently, and a supermassive black hole producing intense radiation. The galactic edge is sparse, with fewer heavy elements available for rocky planets and life. Earth exists in a sweet spot, the galactic habitable zone, where conditions are moderate enough for life to develop over billions of years. Ward and Brownlee catalogued over a dozen such factors, each of which might be necessary for complex life, and each of which might be rare. Even if each factor has a 10% probability of being satisfied, the combined probability of all factors being satisfied would be 1 in a trillion. If Ward and Brownlee are correct, then the great filter lies primarily in our past. We are alone because the path to intelligence is nearly impossible to traverse. The universe is empty not because civilizations destroy themselves, but because they almost never arise. This should comfort us. It should mean our future is bright. But here is the problem. Oxford philosopher Nick Bostrom, director of the Future of Humanity Institute, has argued that we should desperately hope the filter is behind us. In a 2008 paper titled, "Where Are They? Why I Hope the Search for Extraterrestrial Life Finds Nothing," Bostrom explained the terrifying implications of finding life elsewhere. If we were to discover even simple bacterial life on Mars, independent of Earth life, it would suggest that the origin of life is not the filter. If life can arise twice in the same solar system, it probably arises frequently throughout the cosmos. That would mean the filter must be somewhere else, somewhere after the emergence of life. The logic is mathematical and merciless. The great filter, whatever it is, must be sufficient to explain why the universe appears empty despite the vast number of opportunities for life to arise. If we eliminate abiogenesis as the filter by finding that life arose independently on Mars, the remaining steps in the path to technological civilization must compensate by being even more improbable. As Bostrom puts it, the filter is so powerful that even with billions of potential starting points, zero civilizations have become detectable. If life is common, then something else must be filtering with extreme efficiency. If we were to find complex multicellular life on Mars, that would be worse. It would mean neither abiogenesis nor the evolution of complexity is the filter. The filter would have to come later still, after the emergence of complex organisms. And if we were to find fossils of intelligent creatures, species that built tools, and perhaps even primitive civilizations, Bostrom wrote that this would be the worst news ever printed on a newspaper cover. It would mean the filter almost certainly lies ahead of us, not behind us. It would mean something destroys civilizations after they reach technological sophistication. Bostrom's argument does not prove the filter is ahead of us. Finding Martian life would not doom humanity, but it would shift our probability estimates in a dark direction. The more steps we confirm are easy, the more the filter must concentrate in the remaining steps. And if those remaining steps are in our future rather than our past, we should be very, very worried. This is why the silence of the universe cuts both ways. The absence of detectable civilizations is consistent with the filter being behind us, in which case we are rare but safe. But it is equally consistent with the filter being ahead of us, in which case civilizations regularly reach our level of development and then perish before they can spread to the stars. The question becomes, what could constitute such a filter? What could reliably destroy every technological civilization that arises throughout the universe, across billions of years and trillions of worlds? History provides uncomfortable clues. Consider the Permian-Triassic extinction event 252 million years ago. In a span of less than 100,000 years, somewhere between 81 and 96% of all marine species vanished. Approximately 70% of terrestrial vertebrates were wiped out. It remains the only mass extinction that devastated insect populations. Scientists call it the Great Dying. The cause appears to have been volcanic activity in what is now Siberia. Massive eruptions that released enormous quantities of carbon dioxide and sulfur dioxide into the atmosphere. Global temperatures rose by approximately 8 degrees Celsius. The oceans acidified and lost dissolved oxygen. Ultraviolet radiation reaching the surface increased as the ozone layer was damaged. Recent research from the University of Bristol suggests the devastation was so complete that for millions of years afterward, the same few survivor species dominated every ocean on Earth, from equator to poles. Recovery took 5 to 10 million years. For perspective, modern humans have existed for roughly 300,000 years. Our entire species could have risen and fallen 30 times over in the span it took Earth's ecosystems to recover from one catastrophe. Earth has experienced at least 5 such mass extinctions, and possibly many more. The Ordovician-Silurian extinction, 444 million years ago, killed 85% of marine species, possibly triggered by a gamma-ray burst from a nearby supernova, stripping away Earth's ozone layer. The late Devonian extinction eliminated 75% of species over a 20 million year period. The Triassic-Jurassic extinction, 201 million years ago, cleared the way for dinosaurs to dominate. The Cretaceous-Paleogene extinction, triggered by an asteroid impact 66 million years ago, ended the age of dinosaurs and allowed mammals to rise. Each of these events came close to sterilizing the planet. Each of them was natural, requiring no intelligence, no technology, no failure of wisdom. The universe is capable of destroying life through sheer indifference. But notice something. Despite 5 mass extinctions, despite the near total collapse of ecosystems multiple times, life persisted. It recovered. It evolved new forms to fill the emptied niches. The filter represented by natural catastrophes, while severe, was not absolute. Technological civilizations face additional risks they create themselves, and these risks may be far more severe. On October 27, 1962, during the Cuban Missile Crisis, Soviet submarine B-59 was subjected to depth charge attacks by American destroyers. The submarine lost contact with Moscow and believed war might have already begun. The captain wanted to launch the vessel's nuclear torpedo. Launch required agreement from 3 officers. 2 agreed. The third, Vasily Arkhipov, refused. If Arkhipov had agreed, the torpedo would have destroyed the American fleet. The United States would likely have retaliated with nuclear weapons. The Soviet Union would have responded in kind. Hundreds of millions might have died in the initial exchange, and billions more in the nuclear winter that followed. This was not the only time. In 1983, Soviet early warning satellites detected what appeared to be 5 American intercontinental ballistic missiles launching from Montana. The system's protocols called for immediate retaliation. Duty officer Stanislav Petrov, alone in a bunker in the middle of the night, made a decision that violated every protocol. He reported the detection as a false alarm without verification. He reasoned that an American first strike would involve hundreds of missiles, not 5. He was right. A software glitch had misinterpreted sunlight reflecting off clouds. In 1995, Russian radar operators tracked what appeared to be a submarine-launched ballistic missile rising from the Norwegian Sea toward Moscow. President Boris Yeltsin was awakened and presented with his nuclear briefcase. For several terrifying minutes, he prepared to authorize retaliation. The missile was actually a Norwegian scientific rocket studying the aurora borealis. Norway had notified Russia of the launch weeks earlier, but the message had not reached the radar operators. We narrowly avoided nuclear catastrophe more than a dozen times during the Cold War, often through pure luck rather than wisdom. The weapons that nearly destroyed us in the 20th century have not disappeared. Approximately 12,500 nuclear warheads still exist, roughly 90% of them held by the United States and Russia. The explosive yield of modern thermonuclear weapons is measured in megatons. The Hiroshima bomb was 15 kilotons. A single modern warhead can be 1,000 times more powerful. The largest weapon ever detonated, the Soviet Tsar bomber, in 1961, had a yield of 50 megatons, over 3,000 times the Hiroshima bomb. Climate models developed by researchers including Carl Sagan, Richard Turco, and Alan Robock suggest that a full-scale nuclear exchange would inject enough soot and debris into the stratosphere to trigger nuclear winter, potentially reducing global temperatures by 10 to 20 degrees Celsius for years. Sunlight would be blocked, photosynthesis would largely cease, agricultural systems would collapse. Even a limited regional nuclear war between India and Pakistan, involving perhaps 100 warheads, could inject enough smoke into the atmosphere to reduce global food production by 20% for years, potentially triggering worldwide famine. Nuclear weapons have existed for only 80 years. For how long can any civilization maintain the stability required to avoid using such weapons? 1,000 years? 10,000? 1,000,000? The Drake equation, formulated by astronomer Frank Drake in 1961 for the first scientific meeting on the search for extraterrestrial intelligence, includes a term L, representing the average lifetime of a communicating civilization. At that meeting at Green Bank Observatory, physicist Philip Morrison, who had worked on the Manhattan Project, grew somber. He estimated that if civilizations typically destroy themselves within a decade of developing radio technology, there might be only one communicating civilization in the galaxy at any given time. If L is small, the filter is us. There is a pattern in all these risks that we cannot ignore. Nuclear weapons appeared in 1945. Climate change became undeniable by the 1980s. Genetic engineering capable of creating novel pathogens emerged in the 1990s. Artificial intelligence began its current, explosive growth in the 2010s. Each decade seems to add new ways for humanity to destroy itself. This is not coincidence. It is a consequence of the nature of technology itself. Scientific knowledge accumulates. Each generation inherits all the discoveries of previous generations and adds more. The power to manipulate matter and energy grows exponentially. But wisdom does not accumulate in the same way. Each generation must learn ethics, cooperation, restraint from scratch. Our institutions evolve slowly, if at all. Our instincts are those of savanna primates, optimized for small group social dynamics, not for managing existential risks to a global civilization. This creates a gap between our power and our wisdom that grows larger with each passing decade. We can do more than we understand. We can build systems whose consequences we cannot predict. We can unleash forces we cannot control. Perhaps this gap is the great filter. Perhaps every civilization that develops technology inevitably reaches a point where its power outstrips its wisdom. And the only question is whether it closes that gap before catastrophe strikes. But nuclear war is not the only self-inflicted existential risk we face. In fact, it may not even be the most serious. Climate change represents a slower, but potentially equally devastating threat. The IPCC has identified tipping points in Earth's climate system that once crossed could trigger runaway warming processes. The collapse of the West Antarctic ice sheet, which holds enough water to raise sea levels by over 10 feet, may already be inevitable. The Amazon rainforest, which has historically absorbed carbon dioxide and moderated global climate, shows signs of approaching a threshold beyond which it could transform into savanna, releasing its stored carbon and accelerating warming. The permafrost regions of Siberia and Alaska contain twice as much carbon as is currently in the atmosphere. As they thaw, they release methane, a greenhouse gas 80 times more potent than CO2 over a 20-year period. These processes could reinforce each other in cascading feedback loops. Warming melts ice, which exposes darker ocean water, which absorbs more heat, which melts more ice. Warming thaws permafrost, which releases methane, which causes more warming, which thaws more permafrost. Once such cycles begin, they may be self-sustaining and effectively irreversible on human timescales. The current concentration of carbon dioxide in Earth's atmosphere is approximately 420 parts per million, higher than at any point in at least 800,000 years and rising rapidly. Before the Industrial Revolution, it was around 280 ppm. During the Permian-Triassic extinction, CO2 levels reached approximately 2,500 ppm. We are not there yet, but we are on a trajectory. Climate change alone is unlikely to cause human extinction. We are an adaptable species with powerful technology, but severe climate disruption could cause billions of deaths, collapse global trade networks, trigger mass migrations and resource wars, and destabilize the institutions that prevent other existential risks from manifesting. A civilization struggling to feed itself is not a civilization investing in asteroid defense or AI safety research. Then there are the technologies we are only beginning to develop. Artificial intelligence is advancing at a rate that has surprised even its creators. Large language models, once a curiosity, now assist in scientific research, write code, and influence public discourse. The capabilities of AI systems are increasing by orders of magnitude each year. A 2023 statement, signed by leading AI researchers and CEOs, including Turing Award winners, stated that mitigating the risk of extinction from AI should be a global priority alongside other societal scale risks, such as pandemics and nuclear war. The concern is not science fiction robot uprisings. The concern is that we might create systems whose goals are subtly misaligned with human values, systems intelligent enough to pursue those goals effectively, but not wise enough to question them. A system optimizing for a narrowly defined objective might take actions harmful to humans, not out of malice, but out of indifference, the same indifference with which a construction company demolishes an anthill to build a parking lot. Consider what has already happened. In 2016, Microsoft released an AI chatbot called Tay on Twitter. Within 24 hours, it had been manipulated into producing racist and hateful content. In 2023, a developer used GPT-4 to run an autonomous agent called Chaos GPT, explicitly aimed at destroying humanity. The agent compiled research on nuclear weapons and attempted to recruit other AI systems. It failed only because current AI lacks the capability to execute such plans. But capabilities are increasing. Autonomous weapon systems, drones capable of selecting and engaging targets without human intervention, already exist. A Turkish-made Kargu-2 drone reportedly became the first lethal autonomous weapon used in combat during the Libyan civil war in 2020. The integration of AI into military systems is accelerating. What happens when the decision to launch a nuclear weapon must be made in seconds rather than minutes, too fast for human deliberation? Biotechnology poses similar risks. Gain-of-function research in which pathogens are deliberately made more transmissible or deadly to study them could result in the accidental release of engineered diseases. The COVID-19 pandemic killed millions and may have originated from a natural spillover event or a laboratory accident. The question remains unresolved. What is certain is that laboratories around the world contain pathogens far more deadly than SARS-CoV-2. The technologies that allow us to sequence genomes also allow us to synthesize them. The knowledge required to create novel pathogens is becoming more accessible. In 2002, researchers at Stony Brook University synthesized the polio virus from scratch using publicly available sequences. In 2005, the genome of the 1918 influenza virus, which killed an estimated 50 million people, was reconstructed and published. A sufficiently determined actor with sufficient resources could potentially engineer a disease optimized for transmissibility and lethality. Unlike nuclear weapons, bioweapons require no industrial infrastructure, no enriched uranium, no missile systems. They require knowledge, which cannot be uninvented. Every advance in our technological capabilities is also an advance in our capacity for self-destruction. The same tools that extend our reach into the cosmos can turn inward. This is where the great filter reveals its terrible geometry. The path to becoming a spacefaring civilization capable of colonizing other worlds requires precisely the technological capabilities most likely to destroy a civilization before it achieves that goal. You cannot build interstellar spacecraft without mastering nuclear physics. You cannot cure diseases without understanding genetics. You cannot create artificial intelligence without creating artificial intelligence. Every civilization that develops technology capable of reaching the stars must first pass through a period in which it possesses technology capable of destroying itself. This is not a coincidence or bad luck. It is a logical necessity. The same scientific principles that enable space travel enable weapons of mass destruction. Robin Hanson, in his original Great Filter essay, noted that the filter could consist of one extraordinarily improbable step or many moderately improbable steps compounding together. The math works out similarly either way. But the implications are different. If the filter is one step, we might be able to identify it and potentially avoid it. If the filter is many steps, any one of which could destroy a civilization, then even if we survive one existential risk, another awaits, and another after that. The gauntlet might be endless. Perhaps every civilization in the universe reaches a bottleneck, a period in which it possesses the power to destroy itself, but has not yet developed the wisdom, the stability, the institutions required to survive that power. Perhaps this bottleneck is extraordinarily narrow. Perhaps the window between developing nuclear weapons and developing sustainable interstellar travel is 1,000 years or 10,000, and the probability of surviving that window intact is infinitesimally small. The physicist Herman Kahn, thinking about nuclear strategy in the 1950s and 60s, coined the concept of a doomsday machine, a device that would automatically destroy all human life in retaliation for a nuclear attack. Kahn intended it as a thought experiment to illustrate the absurdity of nuclear deterrence carried to its logical extreme. But in a sense, every technological civilization builds doomsday machines. The weapons exist. The knowledge exists. The only question is whether the species develops the wisdom not to use them. The SETI Institute's Jill Tarter once compared 60 years of searching for extraterrestrial signals to scooping one 8-ounce glass out of Earth's oceans and concluding, upon finding no fish, that the oceans must be empty. A 2018 paper by researchers at Penn State calculated more precisely. We have searched roughly the equivalent of a hot tub's worth of water from Earth's oceans. The cosmic haystack is vast beyond comprehension. But the Breakthrough Listen initiative, launched in 2015 with $100 million in funding from entrepreneur Yuri Milner, is changing that. Using the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia, researchers are surveying the nearest million stars, the nearest 100 galaxies, and the plane of our own galaxy for signs of technological activity. They generate approximately 24 gigabytes of data per second at Green Bank alone. Sophisticated algorithms search for narrowband signals, the kind of transmissions that only technology could produce. They have found nothing. The Allen Telescope Array, designed specifically for SETI and jointly built by the SETI Institute and UC Berkeley, listens continuously from its location in Northern California. China's FAST telescope, the largest radio dish in the world at 500 meters in diameter, includes SETI among its core mission objectives. The search is accelerating. The tools are becoming more powerful. The fraction of the cosmic haystack we have explored is growing. And still, silence. Astronomer Seth Shostak estimates that if intelligent life exists in significant numbers within 1,000 light-years of Earth, there should be at least 30,000 planets hosting civilizations capable of radio transmission. We have not detected a single one. The silence grows louder with each year of searching. Each null result pushes the filter, wherever it lies, toward greater severity. The math demands that something is preventing civilizations from becoming detectable across interstellar distances. Either they almost never arise, or they almost never survive. There is another possibility we must consider, one that sits uncomfortably between hope and despair. Perhaps civilizations do survive, but they do not expand. Perhaps the dream of spreading across the galaxy, which seems so obvious and compelling to us, is something mature civilizations abandon. Perhaps they turn inward, becoming virtual beings living in simulated realities, consuming minimal resources, leaving no cosmic footprint. Perhaps they achieve a kind of enlightenment that makes galactic colonization seem as primitive and pointless as conquest seems to us compared to our ancestors. This is the zoo hypothesis and its variants, the idea that advanced civilizations exist but choose not to interfere with developing species like ours, or choose to exist in ways we cannot detect. It is not impossible. We cannot rule it out, but it requires a remarkable uniformity of behavior. If even one civilization in the history of the galaxy decided to expand, decided to build Dyson spheres and send out probes, it would leave visible traces. The fact that we see no such traces means either no such civilization has ever existed, or every single one has chosen the same path of invisible existence. Nick Bostrom calls this the convergence problem. For the zoo hypothesis to explain the silence, we need virtually all civilizations to converge on the same behavior. But we know from our own species how diverse civilizations can be. Would every alien culture with different biology, different history, different values all make the same choice? Would none of them want to explore? Would none of them want to leave a mark? It seems unlikely. The simplest explanation for the silence remains the most disturbing one. Either civilizations almost never arise, or they almost never last. We may be alone in the universe. We may be the first. Or we may be one of countless civilizations that arose, flourished briefly, and vanished, leaving nothing behind but cooling ruins and unanswered radio signals that will propagate outward forever into an empty cosmos. The answer to Fermi's question remains unknown. Perhaps we will never know it. Perhaps the universe is so vast that other civilizations exist but are too far away to ever detect or contact. Perhaps they exist but have chosen to remain silent, watching us from afar, waiting to see if we pass the test they also faced. But there is one thing we can know with certainty. Whether the filter is behind us or ahead of us, whether we are rare survivors or doomed inheritors of a cosmic pattern of destruction, what we do matters. It matters to us, to our children, to their children, extending forward into a future that could be unimaginably bright or could end in darkness. If we are the only intelligence in the universe, then we carry a responsibility unlike anything any species has ever borne. We are the universe's only chance to know itself, to appreciate its own beauty, to ask questions about its nature and purpose. If we destroy ourselves, that light goes out, perhaps forever. If we are not alone, if other civilizations exist or existed, then we are participants in a cosmic experiment, one that tests whether intelligent life can survive its own cleverness. Every civilization that arose faced the same test. Most failed. Perhaps all failed. The question is whether we will be different. But here is what we must not forget. The Great Filter is a statement about probability, not destiny. It tells us that the path we are on is dangerous, that civilizations similar to ours have likely failed many times throughout cosmic history. It does not tell us that failure is inevitable. We are the first known species in 4 billion years of evolution on this planet to understand our own precariousness. We are the first to comprehend the risks we face. We are the first to have the ability, in principle, to choose a different path. Consider what we have already survived. During the Cold War, the United States and Soviet Union accumulated over 70,000 nuclear warheads between them, enough to destroy civilization many times over. Today, that number is around 12,500, still catastrophic but declining. International treaties, arms control agreements, and improved communication have reduced the risk, though not eliminated it. We have developed early warning systems for asteroid impacts. NASA's Planetary Defense Coordination Office tracks near-Earth objects and develops technologies to deflect any that threaten our planet. In 2022, the DART mission successfully altered the orbit of the asteroid Dimorphos, demonstrating that we can protect ourselves from the kind of impact that killed the dinosaurs. We are developing the ability to spread beyond this single world. SpaceX is working toward a permanent human presence on Mars. NASA's Artemis program aims to return humans to the moon as a stepping stone to deeper space. Private and government programs are developing the technologies that could eventually enable interstellar travel. This knowledge is not cause for despair. It is cause for urgency. Every day that we survive without nuclear war, we gain another day to develop institutions that reduce the risk of nuclear war. Every year that artificial intelligence advances without catastrophe, we gain another year to understand how to align it with human values. Every decade that we continue to exist, we grow our civilization's resilience, diversify our presence beyond this single fragile world. The philosopher Toby Ord, author of The Precipice, Existential Risk and the Future of Humanity, estimates that the probability of human extinction within the next century is approximately 1 in 6, roughly the odds of Russian roulette. This is terrifying, but it also means the odds favor survival, if only barely. And those odds are not fixed. They depend on what we do. Nick Bostrom has argued for the establishment of institutions focused on existential risk mitigation, organizations that study threats to civilization and develop strategies to address them. The Future of Humanity Institute, which he founded at Oxford, is one such organization. The Center for the Study of Existential Risk at Cambridge is another. These institutions represent humanity beginning to take seriously the threats we face. We have, for the first time in history, the tools to rationally assess and address existential risks. We can model climate change. We can monitor asteroids. We can study the dynamics of nuclear deterrence. We can research the alignment problem in artificial intelligence. We can develop early warning systems for pandemics. We can diversify our presence beyond Earth. None of this guarantees survival. The filter, whatever it is, has presumably claimed civilizations more advanced than ours. Civilizations that also thought they understood their risks. Civilizations that also took precautions. Perhaps they made mistakes we cannot yet imagine. Perhaps they face threats we have not yet encountered. Perhaps the universe simply contains dangers that no amount of foresight can avoid. But we have something those failed civilizations may not have had: knowledge of the great filter itself. We know we are in danger. We know the stakes. We know that the silence of the cosmos is telling us something important about the path we are on. Robin Hanson, who first formulated the great filter concept, has suggested that understanding the filter is itself a critical step in passing through it. A civilization that knows it is at risk may behave differently than one that does not. Self-awareness is not sufficient for survival, but it may be necessary. And if we survive this century, if we develop the wisdom to match our power, if we expand beyond this single planet, then the great filter, wherever it lies, will be behind us. We will have threaded the needle. We will have become what no other civilization, as far as we can tell, has ever become: a species that did not destroy itself. The universe is 13.8 billion years old. Earth is 4.5 billion years old. Modern humans have existed for 300,000 years, civilization for 10,000, nuclear weapons for 80. The technological era is the blink of an eye. Perhaps we are too young to judge. Perhaps civilizations do survive, but we are simply among the earliest, arising in a universe that has not yet had time to fill with life. Perhaps the first civilizations to achieve interstellar presence are the ones that shape the future of the cosmos, and we are candidates for that role. This possibility deserves careful consideration. The universe is old, but it may not yet be mature. Stars will continue to form for trillions of years. If we survive, if we spread, we could seed life throughout the galaxy and beyond. We could become the ancestors of a civilization that endures until the last stars burn out. Or perhaps not. Perhaps the filter is ahead, implacable and patient, and everything we build is merely arranging deck chairs on a cosmic Titanic. Perhaps 1 million civilizations have stood where we stand, looked up at the same stars, felt the same hope, and then vanished without a trace. But consider what it would mean if we succeed. If humanity survives this century, if we spread to Mars and then to the moons of Jupiter and Saturn, if we develop the technology to travel between stars, if we seed life on worlds orbiting distant suns, then in 1,000,000 years, in 1,000,000,000 years, our descendants will look back at this moment, at this century, at these fragile decades when everything hung in the balance. They will know that once, long ago, on a small blue world orbiting an ordinary yellow star, a species arose that was clever enough to destroy itself and wise enough not to. They will know that the Great Filter was real, that it had claimed countless civilizations before, and that somehow, against all odds, their ancestors made it through. We could be the beginning of something that fills the galaxy with life. We could be the ancestors of beings we cannot imagine, living lives we cannot comprehend, on worlds we have not yet discovered. Everything that happens after this, for billions of years, across trillions of worlds, depends on what we do in the next few generations. But consider this: if we are doomed, if the filter is certain and inescapable, then nothing we do matters anyway. We might as well have hope. We might as well try. The effort costs nothing against the alternative. And if we are not doomed, if survival is possible, then what we do now, in this century, might be the most important thing that any beings have ever done anywhere in the universe. We might be the ones who make it through. We might be the ancestors of a civilization that spreads across galaxies and endures for billions of years. The universe does not owe us survival. It does not owe us meaning. It does not owe us hope. These things exist only if we create them. The cosmos is silent, but that silence is not a sentence. It is an invitation. It says, the stage is empty. It says, no one else is here. It says, you could be the first. The silence of the cosmos is not a verdict. It is a warning. It says, be careful. It says, others have failed. It says, you are not guaranteed anything. But it also says, someone has to be first. Why not us? When Enrico Fermi asked, where is everybody? He was not making a prediction. He was asking a question. The answer depends on what we do next. Think about what it means to be here, now, at this moment in cosmic history. The universe is 13.8 billion years old. For roughly 13.5 billion of those years, the cosmos was empty of anything that could wonder at itself. Stars burned and died, galaxies formed and merged, planets condensed from clouds of dust, and none of it knew it existed. The universe was a vast machine, running perfectly and meaninglessly through the void. Then, on one planet, orbiting one ordinary star, in one ordinary galaxy, something happened that may have happened only once. Chemistry became biology. Biology became complexity. Complexity became awareness. And suddenly, for the first time in 13.5 billion years, the universe could see itself. We are that seeing. We are the cosmos looking at itself with wonder and terror and hope. We are the means by which the universe knows it exists. Whether we are alone in this role or one of countless such awakenings, we cannot say. But we are here. We are aware. And we face a choice. The philosopher Carl Sagan, who spent his career searching for signs of life beyond Earth, understood this responsibility. In his 1994 book, Pale Blue Dot, reflecting on an image of Earth taken by Voyager 1 from 3.7 billion miles away, he wrote, "There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we have ever known." Sagan searched his entire life for evidence that we are not alone. He never found it, but he never stopped hoping. never stopped looking, never stopped insisting that the question mattered. You are sitting somewhere right now, having read these words. Tomorrow will come. Next week will come. Next year might come. A century from now, your descendants might look up at the stars from a base on Mars, or from a ship traveling to Alpha Centauri, or from a restored Earth where the existential risks of the early technological age are historical curiosities taught in schools. Or they might not exist at all. And Earth might be a silent rock orbiting an unremarkable star, and some future alien astronomer might look at our dead world and wonder why nobody ever answered their signals. The great filter is real. The question is whether we are through it. The universe has given us no guarantees. It has given us only a chance. What we do with that chance is the only thing that has ever mattered. Look up at the sky tonight, if you can. The light reaching your eyes from those distant points has traveled for years, decades, centuries, millennia to arrive at this moment. Some of it left its source before humans existed. Some of it left before Earth existed. You are seeing the past, frozen in photons, crossing the void to meet your eye in this instant. Those stars are suns, each one potentially hosting planets, each planet potentially hosting life. Or not. We do not know. The universe keeps its secrets well, but this much we know. We are here. We exist. We are aware. Against odds that may be infinitely long, chemistry became biology. Biology became complexity. Complexity became us. We are the universe's way of knowing itself, and that knowledge comes with a terrible responsibility. We may be the universe's only hope, or we may be one failed experiment among countless others, soon to join the silence that surrounds us. The choice is ours. The time is now. The great filter is either behind us or ahead, and the silence waits to see which way we fall.